My name is Kelvin Govius. I work at Asmat Technology, and I would like to share with you this presentation on accelerating encryption for solid-state storage devices. We will start out by discussing the benefits of hardware acceleration for solid-state storage devices, and then go on to RISC-V based hardware acceleration. As the read and write speeds for solid-state devices are increasing, there's also a motivation for providing encryption and decryption for self-encrypting drives, and hardware acceleration allows you to maintain those read and write speeds. The RISC-V based hardware acceleration is a motivation at this point because of the growth of the RISC-V ecosystem and hardware, and the ease of attaching a hardware accelerator to a RISC-V system, which wasn't there in prior ISAs. We will then discuss the options for attaching the hardware accelerator, the accelerator microarchitecture, the status, and future work. If you have comments or questions, please post them in the Slack channel and we will try to answer them. This block diagram sets the context for the remaining discussion. And it's a simplified block diagram showing the host system on the left, the memory PCIe bus in the middle, and the storage device on the right. The PCIe bus is an example of a peripheral bus that connects the host to the storage device as well as to memory shown above. And on the bottom, there's I/O devices as well as a traditional hardware accelerator for crypto, which can be added in certain systems. That's labeled as ACC. So some of the terminology: LLC is a last level cache, UC is a microcontroller. The host system consists of a processing cluster with multiple CPUs connected using an interconnect, typically a coherent interconnect, for example, CHI, and a last level cache implemented as multiple slices, one per CPU, connected to a system bridge. And then going over to the PCIe bus, the host can access memory, which is DRAM, and it can also do I/O transactions as well as configure this accelerator. So this would be more of an existing system. Now going into the storage device, consists of the microcontroller, which is labeled as UC, with its own local DRAM. And on the right, the NAND storage devices, which could be multiple of those. So host-based encryption is encryption that's formed by the host. That's the most common encryption. In the context of a data center, for instance, encryption can be performed by the user through software libraries such as OpenSSL, or through the kernel through APIs such as /dev, /crypto, and Linux. To improve the throughput of the encryption and decryption, in the past, crypto instructions were added. These, x86 and ARM added crypto instructions many years ago. RISC-V is in the process of doing so. They've already ratified the scalar crypto instructions. These run on these just to either 32-bit or 64-bit data, and are one element per instruction. They're prefixed with the ZK prefix. They were ratified in October 2021, but because they were so recent, they may not be available in silicon for the RISC-V cores. RISC-V Foundation is also working on vector crypto instructions, ZVK star. These are in public review, but not yet ratified. These would be implemented on a RISC-V processor with a vector unit that supports the RISC-V vector extension. So the common case would be the host would be running either a software library, or it would be running crypto extensions to do encryption and decryption. Now, moving on to the storage-based encryption. The encryption can be performed by the storage device itself. This provides an additional level of security for data that is not encrypted by the host. And the keys would be stored in the storage device and not on main memory, which could improve the data security. The context of doing this would be, for instance, a self-encrypting drive where it's providing an additional level of security, where if the drive is lost, its data cannot be accessed, unless you have the password. So it's providing an additional level of security over and above what the host can do. Now, in the context of the storage-based encryption, we can discuss hardware versus firmware. So a firmware solution would be running on the microcontroller in the storage device. And it, again, could be using either a software library, or it could be using crypto instructions running on the CPU of the microcontroller. So when we use the term hardware, it's specifically referring to a hardware accelerator in this context that's running, that's attached to the microcontroller. This accelerator can improve the throughput and power efficiency of encryption and decryption. It can increase the encryption read and write throughput relative to firmware. It may also be faster than both, not only just a firmware software library, but also firmware routines using crypto extensions. And finally, the RISC-V instruction set and ecosystem makes it easier to attach a hardware accelerator to a RISC-V based controller. And we'll see how to do that. Some of the options next. Some more benefits. It allows offload of the encryption decryption from the microcontroller core onto the accelerator, allowing the controller itself to focus on flash translation level functionality, such as logical to physical block address mapping, where leveling and garbage collection, which is just needed to maintain the quality of the flash device. And it also, one of the reasons why it's more power efficient is it cuts down on power dissipated when running a software library due to fetch, rename, dispatch, and scheduling for the out-of-order core. Here is a updated block diagram showing the hardware, the ASME technology hardware accelerator, just to differentiate it from the traditional hardware accelerator labeled ACC. We're calling this the HWA. It's the light blue block diagram that's inside now the microcontroller. It's attached to it. So there are two options for the attachment, but Please keep this block diagram in mind because the rest of the presentation will be focusing on the block called UC, and we'll show an expanded block diagram. So here are the two types of attachment. One is tightly attached. Here, the HWA is attached inside the microcontroller CPU. The microcontroller could have one or more CPUs. Any one or more of them could have this HWA attached to it. Typically, this would attach to either the load store interface as an additional pipe, or it could attach directly to the private L2 interface. This option is supported for RISC-V CPUs, which have a license which allows integration of an accelerator or addition of custom instructions. For instance, there are companies which offer RISC-V cores with a custom accelerator interface. For example, the Sci-Fi has a core with a interface called VCIX to connect either a vector coprocessor or an accelerator. So the tightly attached option would be a candidate for a CPU with that interface, for instance. Going on to the closely attached option, here the HWA would attach to the interconnect of the microcontroller SoC, and it would be able to then access the last level cache and load or store memory to the last level cache. It would also allow the HWA to participate in a coherency protocol such as AXI or CHI as a non-caching node. Either config allows the firmware running on the microcontroller to configure the accelerator. So instead of the firmware actually running the instructions to do the encryption, it would do some minimal instructions to configure the accelerator, then start it. The accelerator would then take over, perform its own memory accesses, reading from the storage device, writing to memory, or reading from memory, writing to the storage device, and finish the computation, and then inform the code. So here is the updated zoomed-in block diagram of the microcontroller now. Inside it, it looks similar to the block diagram of the host, but that's because it's still just the SoC. It could have one CPU, or it could have maybe two or more. Again, a last level cache, interconnect, system bridge, but in this case, it's connecting to the local DRAM of the storage device and the NAND devices. So the tightly attached would connect via the load store interfaces or the L2. Now going on to there are three interfaces, major interfaces for the tightly attached that would be exposed by the accelerator. One is a management interface. Here, firmware can use RISC-V, just regular RISC-V instructions. So you would have read and write special register CSRs to configure, start, and stop the accelerator. Then there's a memory interface where the accelerator can initiate its own reads or writes to the L1 or L2 caches, depending on how you configure the attachment. And then finally, the completion interface, which can either be synchronous or asynchronous. If it's synchronous, firmware would be polling the accelerator through the management interface for a completion, whereas in asynchronous, the accelerator would interrupt the core upon completing its task, or there was detecting an exception. Here's a block diagram, again, of the zoomed in of the microcontroller. This time, the HWA is attached as a pair of the CPU to the interconnect, where it can access, it can initiate its own reads and writes. So it could load in, to decrypt, it could load in from the NAND, right to the and then write into the last level cache, like the decrypted data. Or it could encrypt data from reading it from in DRAM and then writing it out to the NAND device or to the last level cache. Again, the closely attached has three interfaces. The same management, memory, and completion, but for the management interface, instead of using RISC-V special register reads and writes, which are part of the RISC-V ISA, we would use memory mapped reads and writes, which look like RISC-V loads and stores to the IO memory. The memory interface would use the AXI or CHI interface, coherency protocol, and there's parameters in the accelerator to select which protocol you want. For CHI, for instance, the HWA would look like a RNI node, as it doesn't have any caching. And it would allow for encryption or decryption from memory directly into LLC, whereas the last level cache could be in L2, L3, or L4. On the completion interface, it's also similar to the tightly attached, where you can pull or the HWA can interrupt asynchronously. Here's a block diagram now going down into the HWA block. This is true for either option, either tightly or closely attached. On the right, there's a CSR bank. So there's one bank per thread, where a thread is a string, which you could associate with a particular command. And each bank has its own special registers that firmware can read and write, and can do this through either through the special register interface, or tightly attached, or memory mapped IO for memory mapped loads and stores for closely attached. But regardless of how that's done, the banks provide control to start and stop operation on these crypto pipes. So there's N banks, there's P crypto pipes, where P can be between 1 to 8. And the banks can be configured such that these pipes can be mapped to a bank. So for instance, the config register in bank 0 could say all P pipes are mapped to bank 0 for one maximum compute for just one thread, or the pipes could be distributed across these banks. There's a shared memory controller where all the pipes provide load requests and get load returns, or can store requests. The memory controller interfaces directly with the memory subsystem. There's a parameter, HWA num channels, which allows you to configure the number of memory channels. This dotted block is just for a closely attached interface, and it's not needed for tightly attached, where load rec, store rec, and return would be in the same format as that the CPU requires. There's the only other block that's shared is this carryless multiply, which is needed for the AES GCM, encryption, decryption, and it's not in the critical path, so we decided to just share it across pipes. One other feature is compute resources are decoupled from loads. So when loads are issued to the memory subsystem across the pipes, they could be returning out of order. They could have different latencies based on the workload. And so pipes are only allocated to process either encrypt or decrypt data from a load once that load returns. This allows better pipe utilization as you're not tying up a pipe, even though there's loads outstanding and other loads have returned which could use the pipe. These are the different algorithms that are supported. There's AES 128.256, SM4, SM3, SHA-256, 512. The hardware is optimized for AES GCM. With the storage system, the GCM allows you not only just authentication, but also, not just encryption, but authentication. And with a storage system, individual blocks could be tagged with an ID that could be then authenticated using the AES GCM on a block basis. We mentioned about how software can just use regular RISC-V instructions to configure the accelerator. The change that is needed is the actual address space for the special registers needs to be expanded. But other than that, no other new instructions need to be added. The memory region, which can be configured using physical memory attributes, which RISC-V leaves as to the platform to specify. The HLRA has configurability through parameters. Some of these are design time Verilog parameters specifying the interface. Memory interface can be AXI or CHI, the number of crypto pipelines to be 1 to 8. However, at runtime, the number of crypto pipelines, for instance, can be dynamically changed to a lower value. The accelerator is offered as a soft IP, which can be integrated using these input parameters, largely coded using system Verilog. The current status is we're using the AWS EC2 platform to develop the RTL. And the starting point was the RISC-V crypto task groups open source RTL for a 64-bit data path, which was for their scalar extensions, which we expanded to 128 bits. The plan is to use the AWS F1 FPGA platform to test and to get performance stats. Feature improvements: one, update interrupt interface to support the RISC-V advanced interrupt architecture spec, which is now available. Improve the hardware prefetcher to improve the utilization of the pipes. Also investigate susceptibility to differential power analysis attacks, and to add some performance counters to help study pipe utilization and memory throughput. This is just a little more information about myself. And thank you very much for your time. You can contact us either through email or our LinkedIn company profile or my personal profile. I just want to say thank you to Marty and SNIA for helping me with this video and for organizing this conference. Thank you very much.